Yeah, okay, we are good to go.
Okay, so we are waiting for no one. We are good to go. Okay, thank you. So I'm starting. Okay, so I'll start with my general intro. I'm a master's student at IISc Kolkata, a co-op at IBM Quantum, and also a Qiskit advocate now. So, like this thing has nothing to do with why I use Qiskit, but yes, I like other languages also. So, okay, I will just introduce everything on the go now, and let's get started. So, how I was thinking to take this one as from qubit side, not with the quantum mechanics side, because many of you are not familiar with quantum mechanics. You're just starting. So, qubit will be a better platform. What's a qubit? That's the first question. So, I won't go with the definition what mostly people in physics go with. I will just say it's a two-level system. Means uh, you can just call it two element column matrix. That's it. That's a qubit. And from there you can move forward to operations as a two cross two matrix and so on. So that's this is the simple definition of qubit. Yeah. So yep. Um, Let me just see to the second part, quantum over classical. So, why do you think that we should shift to quantum? People, when you will ask this question to quantum physicists, they will give you some answer regarding complexity and how you can decrease resource size and other things. You can see I have even listed my reasons, but the biggest reason I think we are pursuing this one is not to replace classical computing, rather work with it. So saying this word quantum over classical, which I myself wrote over here, is because to get you that, okay, whenever I say this or whenever someone says this, that doesn't mean we want to replace classical computing in the near time. We are just trying to create the best possible way. So that is working with QPU, that is quantum processing unit, CPU, and GPU together. That's one way in which we want to work. And till now, we have just seen CPU and QPU working together, and in some cases also GPU. But right now, nothing of that sort, that all three are working in one program. So yeah, so let me just go through with my reasons. One is that quantum computing, when you use it, it brings down your exponential scale, which goes with classical computing as the number size increases. It brings down to the polynomial scale. It mostly is in quadratic or cubic or something of that kind, but not more than that. And if you go with that, you will always heard this term reversible, or why do you have unitary transform? Unitary basically preserves your reversibility. So in case you just imagine you start a qubit with a H gate, then you put the inverse of that gate, that is H itself, then it will nullify, bring you down to the state you started with. And this system should be in coherence while doing this. So this thing, reversibility, actually helps you instead of destroying the whole system. You just repeat the same operations again, and you are again to zero. So that's what actually results in energy loss, or you can say not energy loss. You can just say it decreases. By energy loss, I don't mean like losing to the environment, but rather less energy as compared to classical system where you destroy the whole state to get to the 0 point. So imagine a electrical circuit. What you do there, once electricity goes into that and it started working, you can't kill that thing. It means you have to switch it off. That is basically disconnecting the circuit. In quantum, it will still be there. You just need to put the gates in again back in the order, but this should be the inverse of the previous one, and then yes, you will be again to zero. So um, like if I you say like you want to check places or go with where do you want to work on quantum circuits. So here are some resources. I will just like go one by one, which I prefer. My preference is mostly this is not my preference list for sure. So I mostly work with the ones which are free, just because I am not convinced to pay $5 just to create a bastion, which you have to if you use Amazon bracket. So I have a little bias with that. Even if I get some a privilege, then also I won't work with that because at the end I have to pay for this, and I don't believe in paying for anything like that. But yes, so rest of the platform, even Regget is the same platform. Uh, Amazon Bracket also kind of uses this backend, but you can also go to their website and try something on your own. But yes, rest of the three are free. So Quantastica or Quark doesn't have a what to say a QPU, but they are just simulators. And Quark is mostly on the programming side. So just if you check Quark, it was created by someone who was a programmer, and then when he left, he just actually left that thing to join Google. But this project, since he made it public till then, he left it public instead of removing it. So it is more of a programmer's view. You can see that there are even function of zeta and all which you can just set it up and uh, work on it. So if I make it this, it's basically sine pi of z. So these power functions and parametric function, this is a kind of complex one. So I use this one for in case I need to decompose a matrix or something like IBM challenge. But yes, so this is the another one. This is like quantumcircuit.com. I use it on daily basis just in case if I have to um, create something. So it has the same way all the gates, more gates I will say, but less than quark. Less than quark, more than IBM quantum experience. And yep, it's also the same. You can just go to simulate. You will get all the angles, possible state vectors, and change it to only possible to know more about it. And uh, it is like most of the things similar to that. But most important feature, what I like is the cross-platforming, which you can do here. Is that say you can go to PyQuil, Quill, and then Qiskit format or Circ, basically Google format. Quest, well, Quest is another format which is actually increasing. It's for Quest computers. TU Delphi, they use it. Instead of Cosm, they also have one more backend. That's this one. Or most important, unitary matrix. So I don't need to write a big code like I have to do in Qiskit to find unitary matrix. I can just go there and see. So this is like what I do. But more than that, there is this Toaster, which is still in the release version. It's the fastest simulator as far as I've heard. So I haven't tried it yet. So it's paid. Yeah. So again, I always stay away from the paid things. Yeah. And then there is IBM Quantum Platform, which I guess most of you might be aware of due to the high publicity going on and everything IBM is trying to get into Indian audience and work with that. So it's the same thing. Just you have multiple screens to work on it, state vector and everything else. So yeah, so this is like three platform which I use. So this is like all about you need to know before you get started. But and even there is one chapter on this one, the case for quantum in Qiskit textbook. You can go there and read the same things. It's just basically it tells you more about complexity and other thing which I don't think is required now because it's more of a sales view, less of a view of from research side. But yeah, now it's demo time. So okay, let me just show you some programs I created. So yeah, this is the one I created to actually work on a H minus ion. What it is, nothing. So you can get this H.ixyz file from any of, uh, there are many chemical chemistry sites which gives you molecular configuration. I will just show you how does this thing look like. Wait a second, I have. Yeah, so this is just why. So one is number of atom in angstrom units, and the position coordinates in 3 dimension. That's a simple thing. And yeah, so then you define charge, multiplicity, basis set, name. These are some like basis set are basically wave function in which you try to expand wave function of a molecule. So don't try to get more of it. Just see that what I'm trying to do here. Here, the biggest issue is how you get Hamiltonian. So here I'm not using Qiskit. This is Penny. So you just go there, run everything, and then see that um, like how this thing works. So um, this one just gives you direct Hamiltonian, and this direct Hamiltonian you can use for it's too small for H. Yeah. So let me just go a bit level high. It looks too easy. So okay. Oh, I have that right. So it should be for helium plus. Hmm. So I don't remember actually basis name. I just find it. All bases are available. You just need to know how they write things. Hmm. I CCO. I was just trying to use this one. Oh, okay. So it worked here. Okay. So it's actually run format of the same basis. CCPVD. I guess no, it's not that one. Sorry. No, it should be. Yep. Now see, this Hamiltonian is actually um, 10 qubits. It's on the top, you can just read it 10 qubits, and a 5 wave function basis set. It's for complex molecules, but you don't need it for basically the one I'm using. Helium is a small molecule, or even helium H plus. But for molecule like such as a higher one, you will need it. Like imagine for caffeine. Caffeine is your uh, day-to-day molecule, but even you can't simulate that. It will be hell higher. This one is too simple, I'm telling you. And then you go one level beyond that. So let's see, move to the smaller Hamiltonian, which we had of H minus. And actually, I just left it on run and see. Just in 4, you can go to the ground state energy. So this one still takes a bit of time. Now you can do the same thing on quantum processor, for which these steps will be just once a go thing. So it took 80 iterations for that. It calculated 80 times the same matrix, applied the same operation, and then done it. Instead, quantum processor can just take this one as qubit input and work on it. There are many more things in this state formation, variational formation, but I will just like step back here. This is a, like your uh, pre-made configuration thing. So you don't need to create much here, but yes, just in case you want to look back and see what I actually did is this. I will just show you one more thing here. So yeah, so this is helium H plus, and it has okay. Just let me write the basis HTO3G. Okay, oh, sorry. I need to run on. Yeah. So this Hamiltonian, and then actually you can reduce this 4-qubit Hamiltonian to 2-qubit Hamiltonian just by reducing uh, number of orbitals, but it is not recommended as this is a small molecule. We don't do that. But just kind of like since I was trying to show you, I did that. And what the result is here. So okay, don't say. Hmm. So this is the one. Like, don't look much into it. I just enable two things. One is quantum classical, which will give me if I go to export and try to get a Qiskit version of it, it will give me everything with a classifier. So here is your optimizer, and you can even convert it into a classifier function. So it gives you a pre-made optimizer. You can modify it and even change it here. I prefer changing it from here. Just choose, I like Kobala, so yep. And tolerance, one more zero over here. You have to define cost function before doing this one. And this is the one I like. This is basically uh, iota z cost function, which is just multiplying identity with a z and then try to map eigenvalues and then you will know. So this is not the thing I should give you in this lecture, but rather in a quantum chemistry lecture. Just let me go through with this thing. So this is your variational form. Alpha 0, beta 0, these all are parameters. So you can just check it out, all those parameters, how it works. And this variational form is actually copied. So you don't need to learn that. You can create anything. I tried to copy from a known variational form, which is UCCHD. So this is from there. So this is how circuit is made. And these circuit are run n times so that you can reach n by n I means number of terms in this Hamiltonian. So uh, if you go, no, this is quite a long one. Let me see. So for this one, where you can see um, only iota, this one doesn't count because you don't run this one. It is identity. So the ones with other than iota counts, iota and something else also. So these all are the number of times you need to run circuit. So you run it thrice with these given parameters, and in this measurement basis, then you get to know what is the uh, number of number of counts. From there, you calculate expectation value and you get value. But these all are like why I'm telling you this one because this is the thing most of the companies are right now using QC for just to simulate molecules. And the biggest reason is that classical computing is still more powerful in this domain as you have more of classical computing resources as compared to quantum computing. But the day we will be able to use a fault tolerant, like completely a zero error or logical quantum computer with 1,000 logical bases, then logical qubits, sorry, not bases, logical qubits, then that day you will be able to simulate higher molecules and actually go to something like that will be the era that you get anything, any new virus or any kind of molecular composition, then you can just find it out that how it is created and then reverse engineer it to create its antidote or anything like that. So that's the dream, and we are slowly moving towards that. But I personally think that this is not the only way. You can also use it for QML, and um, there's a competition which is going to be uh, held in September, I guess. You guys will receive notification. Isaac has been part of the same initiative from IBM side, so we will receive it. And yes, it will be a more in quantum machine learning. So for like questionnaire, as far as I can say, is very nicely prepared. And I will tell you to at least go there, check out, and participate. It's not necessary that you have to win, but you can try. That's what you can do. So it's a simple thing. You just need to look to the question, answer them. I can't say more because there's still time it being declared, but as soon as it get declared, you can just go and say there. It will be soon on social media and everything. But yeah, you guys will receive a link to register from institute side as part of IBM ISO regulations. So that's some future news coming there. And yeah, so QML means machine learning, and then VQE, variational quantum eigensolver, what you see here is that for molecules. And then there's one more thing we actually want to use on it. Some of you who has attended QGSS, you guys must be knowing that, okay, you can use teleportation algorithm, which just teleports your state from one qubit to another qubit so that you can have a secure communication, or RSA encryption or de-encryption. But these all comes in as soon as you have a logical qubit. Like QML and VQE are the only ones who are working right now without the logical qubit. But as soon as we have logical qubit, yeah, it will be better than the current situation. And yeah, so that being said, and since I've given you these resources, which you can just go and find out anywhere. So uh, if you want to find out more and what I used here or anything, you're free to ping me. I will perhaps transfer all of these slides to public GitHub account, my public GitHub or anywhere. I think public GitHub will be good. I guess you guys know how to access GitHub. It's just you go there and download all the codes. No need to install much of things. So yeah, uh, being there, like since I've explained, it's actually not explained you. I tried to show you like what are the things people use in quantum, and it's not about that only physics or only some stream can do it. It's like you saw just now, whatever it was all chemistry over there. So it's quantum chemistry. It also consists physics, chemistry, both of it, but it's not that only one field person can do it. You can always cross refer each other, cross working, or yep, see that in which way you feel comfortable to work in. That's the most important thing here. But I will say that after this all, like telling you which thing you want to use or which you won't, I've seen people trying to pay for QC, learning QC. So I will just say that QC is not in that stage that you need to pay to anyone uh, of like if even it's a startup or of some public venues which is going on, but don't pay until unless there is some justification. If you're paying, that should be something like if you're going to attend an event, that should be event cost in the sense that you need to live there or something like that, staying cost or something. But do not pay for resources. It's all free. It's all everywhere. Just you just need to Google it properly, I will say, then you can get it. And this wasn't the first starting lecture. It was just like I was telling you where you can get resources and another thing. And yes, there are you can just go and play along with these sites. I will perhaps we will have this site up this slides uploaded, and you can use these links. Wait, let me just share my screen. The links I have to show you. Okay. Yeah, so you can use any of these links to create a model for you or started working on it. Um, and I think until unless we start with small computations, you can play on your own. And as soon as we start, we are thinking, I guess Cody has more plans on that, but I think he will also give you a bit of some short algorithms like one qubit teleportation and something of that sort. And yep, you can go good to go with it. So yeah, sorry, questions.
Okay, guys, do we have a question? Uh,
By the way, I just want to clarify whatever you saw right now. If you are in a shock that that thing, yeah, sorry. So do we need to install separate software for working on QC? Separate software? I don't think so. No, you can just go to any of these websites, start working. You will need software at the point when you want to program, hard code anything, go in that site. Until unless, feel free. You can use any softwares. Any not software, sorry, any website to avail those resources. It's all free. Yeah, and I was saying that here what like try to demonstrate, it's just a thing for demonstration. Don't try to be in that you need to learn this or what I was doing. No, it took time for me also, and I guess you also need to take your time working on it. And these are actually small molecule. I think some of the good molecules people have done. Uh, I guess Sabita knows more about it. So,
RO,
Sabita,
yeah.
which is the one you did? I
I
think,
work with the lithium hydride, NH3 ammonia, basically because that's used in fertilizers and it had something to do with optimizing energy resources and something like that. But basically, the computational resources available at currently are not sufficient to simulate bigger molecules. So, like you mentioned, that's an
yeah, I
issue.
agree.
Yeah.
Hmm. Yeah, so as she said, like ammonia and lithium hydride. So yeah, these are the things which are like you can try working on it. But I'll say that before doing this, get more from the side of basics, that how these gates and all work. Later on, you can go into VQA and other things because VQA and all those are like just completed part where you just need to provide the molecule and its composition, and then it will self-calculate everything. But what we are lacking is actually working on the basics, which is important, but rather not useful. So everything is being hard-coded these days. They have modules for everything, but yep, for starts, you need to go through with putting on gates there and seeing what each gate does. It's the rule.
yeah, about the software thing, someone was asking. Uh, when we will be going through the steps, I'll be making sure that all the softwares are available for you guys, like that FiSci. It's called FiSci. Yeah, the FiSci software has been used by Rahul Pratap in that PQE thing. So yeah, we will be providing you the links and the information about the softwares as well.
Okay, just in case you guys want to see the software, since you guys are eager, I will just like drop
Uh,
some link. Uh, just go, like, just have a look in case you want to know more. So yeah, it's not mandatory. You can just go there and see a Quizkit, and then you can have Penny Lane. I use these two. There are more you can actually use. So Penny Lane also has its own its own kind of UI version, so you can go there and use it. It's just for like demo codes or something, but it works, so you can try it.
uh, okay, let's wrap these things up. Okay, so we have any questions, or we will just call it a day? So we are done for the day.
Okay, so see you guys later. Happy remaining part of Sunday. Bye.